Alright, welcome back to ELE 210 circuit theory as we dive into our third equivalent circuits theorem, the superposition theorem. And superposition is a term that's used a lot in electrical engineering, but it always comes down to kind of the same concept. Forgetting about circuits for a second, if we were to look at what are called linear systems, and superposition is an important part of linear systems. Taking a look at our diagram here, if we were to put in a stimulus called x1 of t, some function of time, voltage or current, and another one called x2 of t, another voltage or current as a function of time, and we amplified this one by a factor of a and this one by a factor of b and added them together. If this is a linear system, we'll call it H, what we'll get is the output here will be the output would due to the first stimulus. This is the output of the system to the stimulus x1 of t multiplied by a, this gain factor. You might say, well, this output is also h of, you could say that this is also h of a times x1 of t. Okay, this guy right here, and this guy over here is the same thing as h of b times x2 of t. Well, that makes sense. I mean, we're putting in, if you look at this guy right here, this guy is a times x1 of t, and this guy right here is b times x2 of t. So if I were putting in this guy, x1 of t, multiplying by a, I'd have a times x1 of t, and I'd expect, apart from any of this other stuff, that I would have h of a times x1 of t. There's my input, there's my output. Well, it turns out in a linear system, if I multiply the input by a factor of a, I could take the output of the original signal and multiply it by a factor of a. And we'll look at that down here. That's stated right here. H of a times x of t, in general here, the output of the system due to a scaled input is a scaled output. All right, so you take the output of just x of t and multiply it by a. So the output of any linear system will exhibit scalability. And so if I double the stimulus, if a equals 2, so if I put in twice the input that I normally put in, I'd get twice the output of just that original signal. So double the stimulus leads to double the response due to that stimulus, or triple, or whatever you want. And so, that's how we get this arrangement up here where, h of the scaled input, a times x1 of t, is going to give me, let me make this a little more obvious here. That's going to give me a times the input due to just x of t itself. So scale the input, well, it's going to scale the output. That's part of being a linear system. The other part of being a linear system, and we'll try to adjust this a little bit. The other part of being a linear system is this property called superposition. So, if I were to look at this system, I'm going to put in x1 of t and x2 of t, and I'm going to add them together. So this guy right here, this guy is equal to x1 of t plus x2 of t. I take two signals, add them together, and stick it into the system. So the output here, well, this naturally would be h of x1 of t plus x2 of t So this is the output due to the sum of the inputs, right? There's my input, there's my output. Well, it turns out that the output due to the sum of the inputs is the sum of the outputs or responses if you just had each individual input. They call this superposition, you know. So in this case, if you want to understand what this system does with the sum of two inputs, if you can figure out what it does for x1 of t, and that's, you know, h of x1 of t, and if you can figure out what it does for x2 of t, that's h of x2 of t, you can add those two things together and get the answer. That's in a linear system. So the output of the system in response to the sum of individual inputs is the sum of the system responses to each individual input. And now this is not true in some circuits that where you know, multiplication or you know, funny things happen. They are called nonlinear systems, and we have lots of them. But in signal processing, very often we want to have linear systems because they preserve our signal and they preserve information very well. So there are definitely portions of the signal path which we desire to be very linear systems. Other parts we don't, but there are definitely parts of our signal paths in electronics that we desire to be very linear systems, in which case they should exhibit scalability and superposition. And so we go back up here, and right here we're combining both. These systems exhibit both scalability. See, the factor can be brought right outside of here, and system response is the sum of the responses of the individual signals, and that's superposition. So we have both scalability and superposition. That gives us a linear system. All right. So let's talk about how one applies the superposition theorem. And then we'll look at a kind of circuit where it can really help us. And I'll spill the beans a little bit. We may have a circuit where there are two or more sources and a network or circuit between both of them and the load, or maybe there's 3 or 4 sources or something. Well, superposition, if the system is linear, superposition allows us to go and figure out how much each source contributes to our total output, and then add those outputs up and get the actual total output. So superposition is handy in that way when we have circuits with multiple sources, where you know, a simple total resistance method won't solve it for us. Once in a while we get lucky and we're able to do you know, some kind of Thevenin type thing, and we get lucky with the way the sources are arranged, and we can create a Thevenin or Norton circuit, but that's not typical. So we need this third theorem called superposition to help us deal with those kind of multi-source circuits. So here are our steps. For each source in the system, we deaden all but the selected source. So you pick a source and you deaden all the other sources. Just like in Thevenin's and Norton's theorems, voltage sources become shorts, it's 0 volts, and current sources become opens, that's 0 amps. And so we've done that in Thevenin and Norton's theorem. And then we compute the contribution the selected source makes to the load voltage or load current. Pick one or the other, do not mix. Even if you had some voltages and some currents, if the load is a resistor, you could multiply that resistor by that current and get that voltage. So you do this for each source, and essentially you're going to add up the the contribution of each source and come up with a total, and that's going to be your load voltage or current in that situation. And in resistive circuits, where we've done this with just resistive circuits with arbitrary waveforms, it's okay because you just pick a place on the waveform. I guess you'd have to pick that same point on every source that you're considering, and compute each of their effects on the load. Add them all up, and you'll get the load voltage at that point in time. So, if you had only one funny looking stimulus, then you could do what we've done before and say, hey, I know what the output's going to look like. But if you have a couple different weird waveforms coming in, you might have to compute this a number of times to get enough points to reconstruct what the output waveform will look like. At any rate, we'll do two examples with static DC sources, and then I'll let you kind of extrapolate that in your mind to what it would mean if there were maybe one of those sources were sinusoidal and one were DC. And that's actually a common situation, is you have some transistor or something that's biased with DC voltages to get it to the operating point you want, and then there's a sinusoid going through it, kind of representing the signal of interest. So you have one DC and one sinusoid, but in that case they're easy to add together, and so I don't think it takes a lot of imagination to see how that works. Let's concentrate though on the mechanics of doing a superposition theorem problem. So this circuit I call superposition example 0000. I did that because I created number 1, then I realized I wanted one that was a little bit simpler. So instead of 1 and 2, we've got 0 and 1. Both this circuit and the following circuit have links on Blackboard where you can go and grab projects from my account and run them, and you can find the voltage at the load and see if it matches what we compute. So this is our circuit, all right, and so we have two sources. We have IA equals 1 milliamp up, if you will, all right, and we have V1 is equal to 2.5 volts. So we're going to have to do that procedure where we're going to have to, when we consider V1, we're going to have to deaden IA and figure out what the load voltage is. Then we're going to have to deaden V1 and, using IA, find out its contribution to the source voltage or current. You can do either one, and then add them together and we'll have our answer. Okay, so we'll need to kind of, in our steps, we'll need to consider V1, I think, is the first one. We're going to consider V1 first, so we're going to consider V1, which means we'll have to deaden IA and compute VRL, this is RL1 there, but okay, so VRL, or IRL, either way. And then number 2, I'm going to call that A and B if you like. And then for step 2, we're going to have to consider IA, in which case we'll have to deaden V1, and we'll have to compute VR1 again, or we could compute, VRL or IRL. And then the last thing to do is add together results, because it could be voltages or currents, however you prefer to do it. Add together results from steps, sorry about that. Add together results from steps 1 and 2. Okay, so that's what we're going to do. Okay. So here, this is step 1. We are going to consider V1, and so we deaden IA, which means IA equals 0, and that implies an open. Okay, and you can see right here IA equals 0, and that's your classic open circuit right there. Okay, so this resistor is just dangling off into space, and so no current can flow through it. So we really just have a voltage divider problem with 2.5 volts dropping across R2 and RL, all right, our load resistor. So, so step A, we did that, and step B, we can say VRL is equal to, and the voltage divider rule would go something like V1 times RL over RL plus R2. Well, again, V1 divided by RL and R2, that's the current. It's actually the current that's flowing here, okay? And when you measure that, so V1 over RL plus R2 is the current flowing here. When you multiply that times RL, you get the voltage across RL. And so we'll do that here, if I can manage this correctly. And no, I didn't want that. Okay, there we go. So we know that so this guy is going to be equal to 2.5 volts times, we have a 2.2K load resistor, so that's 2.2K ohms plus 6.8K ohms. All right, and so that's going to be equal to 2.5 volts times 2.2K ohms divided by, well, it's pretty easy to add this. 0.2 in that gives you 7, and 2 more gives you 9. So that's going to be 9.0 k ohms. And we can just forget about the k ohms actually here. And let's see what that's equal to. So I have 2.5 times 2.2 divided by 9. Survey says that I have 611 millivolts, and that's also, you could write that as 0.611 volts. Okay, so we'll remember that number, and then let's go to our next step. This is step 2. Consider IA. All right, so step A, we have to deaden V1, and that means we make it equal to 0 volts, and that implies a short. So here we go, V1 equals 0 volts, which is a short. You can't have any voltage across the short. Alright, so now what we have is we have a current source, and now we're going to compute VRL. Okay, so now we're going to have a current source that's going to flow here, and the current source is going to see R1 in parallel with R2 and RL. So let's do a little computation here. We know that we're going to see 1 mA flowing here. By Kirchhoff's law, if there's 1 mA flowing here, there's no way to get out or into the circuit, so there's got to be 1 mA flowing here. Now that 1 mA is going to split into some current flowing here and some current flowing here. So one way we can determine that is what we care about is the voltage across this load resistor, which is the same as the voltage across this parallel combination. So we know that VRL is also equal to the voltage across RL in parallel with R2. So let's do that calculation. You know, that's going to be, I'm going to use product over the sum like I usually use with 2 resistors. So that's sorry about that. I did it again. RL in parallel with R2 is going to equal 2.2 k ohms times 6.8 k ohms over 2.2 k ohms plus 6.8 k ohms. Again, adding these two together is not very challenging. That's 0.2 on there makes it 7, the 2 makes it 9, so we're going to have or you know, we don't even have to think about that sometimes. In our calculators we can just say 2.2 k times 6.8 k divided by 2.2 k plus 6.8 K. All right, and I got the parentheses in the, whoops, something is not right there. So it's oh, I cleared it, I can't believe I did that. Okay, one more time, it's 2.2 K times 6.8 K divided by 2.2 K plus 6.8 K. There we go. And if we hit enter here, we get that this is equal to approximately 1.66 K ohms. Well, if I have 1.66 K ohms, then VRL, again, actually, let me redraw it just to be more convincing here. I will now have a 1 mA current. This is IA flowing through R1, which is 2.2 K, and then it's flowing through RL in parallel with R2, and that's going to be equal to 1.66 K ohms. Okay, well, we have 1 milliamp flowing here. So, as we said, VRL equals the VRL is equal to the voltage across this parallel combination, because in a parallel circuit, voltage is the same and there are different currents. We just care about the voltage here. So VRL is equal to, at least in this contribution, the voltage of VRL in parallel with R2. And we know that therefore VRL is equal to IA, this current that's flowing, times RL in parallel with R2, and so that's equal to 1 milliampere times 1.66 K ohms. And that's going to be 1.66 volts. The milliamperes is thousandths of an ampere. The K ohms is thousands of ohms. So in essence, the milli and the K cancel each other out, and we just get amps times ohms, which is volts. So we get 1.66 volts. Now, if we go back and look at our other first, step 1, where we consider V1, we got 0.611 volts, and here we get 1.6 volts, and VRL kind of for the whole circuit, this is the VRL from step 1, right? This is, step 2. This is the VRL from step 1. And so we can say that VRL is actually equal to VRL from step 1 plus VRL from step 2. Sorry about that. Okay, and so we can say that it's equal to 0.61, yeah, it's a lot of extra accuracy we probably don't have, plus 1.66 volts. Looks like about well, let's see. We have that guy, and we want to add 0.611. Well, wait a minute, I'm sorry. Let's take 1.66 volts plus 0.611 volts, and we get about 2.27 volts. So, sorry about that, VRL is equal to 2.27 volts, and that is our total solution right there. Now, if I remember correctly, so that's step one. If we were to look at the solution on the if we were to look at the solution on the easy EDA circuits, I think you would find that it says 2.27 volts, and I'll just check my notes here to make sure that everything is proper. And it is indeed, it came out 2.2735 volts, but you could look at that. I'll let you verify that. Now here we have our second example, and it's, sorry, that's a little bit better. Our second example is two voltage sources, and the circuit's just a little more complicated. Got an extra resistor in there. So let's do, we're going to have to consider two sources, so let's see what I considered first this time. Looks like I considered V2 as my first one. Sorry about that, getting the steps kind of different than the way I numbered it, but step one is consider V2. And step A is to deaden V1, which means it will be equal to 0 volts, which implies a short. And step B will be to compute VRL. All right. So, and then step 2, we will deaden V2, because here we're going to, in step 2, we're going to consider V1, obviously. We'll deaden V2. It'll be equal to 0 volts, which implies a short. And we will compute VRL again, and then we'll add those two VRLs together and see what we get. So, what do we have here? This is V1 is equal to 0 volts, which is a short. So this resistor has been shorted out, all right? And so essentially what we have is looking from V2, so this is step 1. Consider V2, and looks like we've already deadened V1 nicely. And step 2, we're going to compute VRL. And again, this is just the VRL due to step 1. But if I look at if I look at this thing now, this guy is essentially shorted out. So what I have, V2 sees, kind of do an R total here. V2 sees R total equal to R4 in series with RL, which will be in parallel with R3, because again, this short here killed R1. So this will be RL in parallel with R3. Okay? So R total is equal to 2.2 k ohms plus 2.2 k ohms times 4.7 k ohms divided by 2.2 k ohms plus 4.7 k ohms. Now from previous problems, well, we can just do this to prove it. 2.2 k times 4.7 k divided by 2.2 k plus 4.7 k, and I get a number that's very close to 1.5 k. All right, so we're going to say we're just going to say that this right here is 1.5 k, and so our total equals 2.2 k ohms plus 1.5 k, and so now we essentially have a series circuit where it's 2.2 k in series with the parallel combination of 2.2 and 4.7, which is this. So VRL in this case, using the voltage divider rule, and I'm going to just say that what we have here now is we have V2 is seeing R4, which is 2.2 k ohms, and here it's seeing RL in parallel with R3, and that's equal to 1.5 k ohms. So to use the voltage divider rule, we would look at this thing and say that VRL in this case is going to be 2.5 volts times 1.5 k ohms divided by 1.5 k ohms plus 2.2 k ohms. All right, and so again, just underscoring the voltage divider rule, 2.5 volts divided by the sum of those two resistors gives me the total current. When I multiply the total current times my 1.5 k ohms here, I wind up with the voltage across this parallel combination, which is also VRL. And of course we can, like we did last time, we can state that fact that VRL is equal to the voltage across VRL in parallel with VR3. I mean, it's always true that the voltage across any one resistor in a parallel combination, you know, this is equal to the voltage across the entire parallel combination, because the voltage is always the same in a parallel circuit. Okay, and so we do a little computation here, and we'll put this down. I'll put it here for now. And we say that 2.5 volts times 1.5 k ohms is, not that you really need to keep the k ohms here, divided by that total 1.5 k plus 2.2 k, and that equals 1.01 volts is what it looks like to me. So this thing says it's equal to 1.0, I think it said 1.0135, so we'll call it 1.014 volts, all right? And that's our result from step 1. We go to step 2. In step 2, we consider V1. In step 2, we consider V1. So, what we have now is a little more complicated circuit. So, step A, we're going to have to deaden V2, and then compute VRL. So here we go. V2 equals 0 volts. Sorry. So, and that's why it's a short. So V1 sees an R total equal to 10, well, let's, I'm sorry, that I could make things go a little longer than I should here. Yeah, V1, let's write it again. V1 sees 10 k ohms. It sees R1 in parallel with R3. Probably should, let's get the symbolic part of it down first. With R3 plus a parallel combination of RL and R4. All right. So the thing is here, though, this voltage, 5 volts, you know, V of R1 is equal to 5 volts, and we got a parallel circuit here, and V of R3 plus RL in parallel with R4 equals 5.0 volts. So in a way, in this case, we don't need to go figure out how much current goes down through R1 and that sort of thing. We know that we have 5 volts you know, from here, we have 5.0 volts from there to there. So we only need to concern ourselves with this portion of the circuit over here. So we know that RL in parallel with R4 is equal to essentially 4.4k ohms in parallel with 2.2k ohms, and we just did that in the last problem, and it's equal to 1.5k ohms. Okay, and now we have 1.5k ohms is what we want the voltage across. Again here, VRL is going to be equal to VRL in parallel with R4, because in a parallel circuit the voltage across any one resistor, VR4, VRL, they're all the same, you know, and so what we're going to use here is the voltage divider rule yet again. And we're going to say that these guys are equal to 5.0 volts times the portion of 1.5k over 1.5k plus 2.2k. Now, I just want to, for the purposes of mathematics here, we just did this with 2.5 volts times 1.5k over 1.5k plus 2.2k. Now we're doing it with exactly twice that. So, you know, instead of 1.014 volts, it should be 2.028 volts. And that's what I'm going to do. I'm going to say it's equal to 2.028 volts. And then VRL for the whole circuit. Here we are, you know, combining steps 1 and 2. VRL is going to be equal to 1.014 volts plus 2.028 volts, and that is going to basically give us 3.042 volts. And I actually got 3.0389 on the simulation, so we're going to declare victory with that. I did a little bit of rounding here and there, but so yeah, 3.038, actually 3.039, so I'm off by 3 millivolts from the simulation, but I think that's a pretty good answer right there. So that's our second example of superposition. And we'll stop there, but do confirm those answers by running those simulations, and hopefully I can put together, all these resistors are in our kits, so you can put together these circuits and make the measurements. You can produce 5 volts and 2.5 volts from the supplies on the A-Down 1000 or M1K, whatever you want to call it, and you can produce a 1 milliamp source by maybe choosing channel A and selecting source current measure voltage as an option, and in which case it will become a current source. And I've actually done that, and the answers do come out correct. You can take, because you can always take channel B and use it to measure voltage and just put it across the, put its probe at the top of the load resistor, and you should be able to read out the voltages correctly. Okay, so that's superposition. We'll have a couple of homework problems related to that, and then we'll declare victory on that, and I will do one more solution with you on what's called simultaneous equations, or the the multi-loop method of solving certain problems. And again, we won't go tremendously deep in that because it would take a lot of time, but it gives you an idea of how circuit simulators actually work. So take it easy, and we'll see you next time. And again, I'll get that lab posted. All right? Bye-bye.